Welcome to Discrete Differential Geometry. Today we're going to introduce the basic object on top of which we're going to define all of our other geometry, and that is a combinatorial surface, or what maybe is more commonly known as a mesh. So people use this word mesh to mean all sorts of things, lots of possibilities. What really is a mesh? Well, for us, we're going to give it a very precise meaning. We're going to study mostly something called a simplicial complex. So simplicial complex is more or less a bunch of vertices and edges and triangles and tetrahedra and higher dimensional analogs. Today we'll talk carefully about the difference between an abstract simplicial complex, which just gives the connectivity of these elements, versus a geometric simplicial complex, which actually says where these elements live in space. We'll also think about questions of orientation and what it means for a simplicial complex to be manifold. So get some really specific definitions for what we mean by a mesh. We'll briefly look at an application to data analysis, and we'll also briefly touch on more general kinds of meshes, cell complexes, in particular something called the Poincare dual of a simplicial complex. And this dual idea is going to be really important when we study discrete exterior calculus. We'll also briefly talk about data structures that can be used to practically encode meshes, in particular adjacency lists, incidence matrices, and half-edge meshes, and talk about the trade-offs between these different possibilities. Now, of course, this is a course on discrete differential geometry. So beyond just talking about meshes as a data structure, we really want to understand what is the relationship between meshes and objects from continuous mathematics. And so really, the object that we're modeling with our mesh is something called a topological space. To really give a proper definition for a topological space takes a little time, and it can be a bit abstract the first time you see it. But very loosely speaking, a topological space, like our mesh, talks about how points are connected up without saying where specifically they are in space. And so by starting out, in this case, on the discrete side, and talking about abstract simplicial complexes, we'll get a very good intuition for what a topological space is like, the fact that it really only talks about connectivity and not geometry, without having to start out with all those detailed definitions. Okay? So let's actually start with something very basic, the notion of a convex set. So people use this word all the time. The shape is convex. What does it really mean? So if you look at a shape, you might actually already have some sense of whether it's convex or not, even if you don't have a very precise definition in your head. So here are just a few examples. We have a star, a triangle, a bottle, a dodecahedron, some blob with a piece cut off, and then just some other blob. Just from looking at these pictures, without getting a formal definition, which of these shapes do you think are convex? I'll let you think about that for a second. Okay, well, of course, to really answer this question, we have to have a definition for what it means for a set to be convex. So here it is. So we'll say a subset S of Rn is convex if for every pair of points P and Q in S, the line segment between P and Q is contained in S. Okay, so just to give a little example, we'll take one of these shapes and we'll take 2 points, P and Q, and in this case we can draw a line segment between those 2 points without leaving the set. Okay, this single line segment alone does not tell us that the set is convex. But if we go ahead and try this same experiment for all pairs of points in this particular shape, we will find that this shape happens to be convex. Okay, how about this shape? Well, not so much. It's pretty easy to see that you can find a couple of points, P and Q, where the straight line segment between them actually leaves the set. So this one is definitely not convex. Okay, so let's return to our examples here. Now that we actually have a definition, which ones are convex and which ones are not convex? Okay, well, it's kind of easier to show that a set is not convex than to show that it is convex. You just have to find a single pair of points that goes outside the set. So for instance, this star is not convex, this bottle is not convex, and this blob is not convex. The rest of them, you can check, are convex, right? It's hard to find or impossible to find any pair of points that makes a segment that goes outside of the shape. Okay? Building on that idea, we have the notion of a convex hull. Okay? So the intuition here is if my shape isn't already convex, maybe I want to wrap it in a convex shape that kind of approximates it. More precisely, we can say that for any subset S of Rn, its convex hull, conv of S, is the smallest convex set containing S, or equivalently, the intersection of all convex sets containing S. Okay, so let's draw a couple pictures just to make sense of that definition. So let's say we start out with this set S. It's got some two-dimensional regions. It's also got some points in it, right? It's the union of all these shapes. And the convex hull of this set, well, it looks like, as I said, wrapping something around this set, kind of making that as small as possible, pulling it tight without becoming non-convex, right? And a different way to think about this convex hull is to take any convex shape that contains S. I've drawn a few overlapping shapes here that are convex and contain S. And if I start intersecting these shapes with each other, then the intersection gets smaller and smaller and smaller and smaller until again I have this tightly wrapped convex hull. Okay? Just to give a concrete example, let's say I give you this set, the set of all points in R3 where the coordinates are either plus or minus 1. So what do you think the convex hull of this set might be? Again, I'll give you a moment to think about that. Okay, well, the first thing to recognize is that these points are the vertices of a cube. And so if we take the convex hull of those points, we get actually the whole solid cube. How do you convince yourself that's the case? Well, you know that you should be able to draw a straight line segment between any 2 points in the set. So maybe what you can start doing is take pairs of points, let's say 2 adjacent corners on the cube. You know that the line segment between those points is contained in the set, so the edges are contained in the set. And now you could connect, let's say, any 2 points on 2 edges of the same face, and that'll kind of fill in the square faces. And then finally take any 2 points on 2 faces, connect those line segments, and you fill in the interior of the cube. Okay, just to give a sense of why is the convex hull of the corners going to be the cube. Now, you could, of course, consider an even larger convex set that contains these points, but that wouldn't be the convex hull, right? We said the convex hull is the smallest such set, which in this case is the cube. Okay, so the reason that we're talking about convex sets is because that lets us give a definition to a really, really important object for us in discrete differential geometry, and that's the idea of a simplex. Okay? So simplex is a kind of fancy word for a very basic idea. So roughly speaking, a k-simplex is, well, depending on the value of k, it's a point for k equals 0, a line segment for k equals 1, a triangle for k equals 2, a tetrahedron for k equals 3. And then if we keep going, this gets a little hard to draw faithful pictures for. Okay, but we get a sense that the number of vertices in this simplex goes up as k increases. Okay, so what really is this? How do we give this a precise definition? Well, let's first go back to an important concept from linear algebra, the idea of linear independence. So you may remember that a collection of vectors v1 through vn is linearly independent if no vector can be expressed as a linear combination of the others. In other words, if there's some collection of real coefficients, a1 through an, such that vj is equal to the sum over all other vectors of those vectors times the coefficients for any vj. Okay, that's a mouthful. Again, maybe we just draw some pictures and the idea becomes clear. So if we have these two vectors v1 and v2, these two sort of anti-parallel vectors, then we say that these are linearly dependent because I can write v2 as just minus some constant times v1, right? I scale down v1 and I flip it in the other direction. v1 and v2, on the other hand, are linearly independent because no matter how much I scale v1 up and down, there's no way to get it to point in the direction of v2. Okay? A closely related idea is the idea of not linear independence, but affine independence. So what does this mean? Perhaps less familiar. Well, a collection of points rather than vectors, p0 through pk, are affinely independent if the vectors vi, defined as pi minus p0, are linearly independent. Right? So I'm going to use linear independence to define affine independence. Okay, so what does this look like? Well, let's consider two sets. We have set A, these 3 points, and we have this set B, these other 3 points. Which one do you think is an affinely independent collection of points? Okay, hopefully this isn't too hard to figure out. So maybe the best thing to do would be to just draw in these vectors vi. So if we draw those vectors in on the left, we get these two vectors v1 and v2. Pretty clearly those vectors are linearly independent. Therefore, the 3 points are affinely independent. Likewise, if we draw the vectors in on the right, we see those look linearly dependent. I can get v2 by just scaling v1. So that means these 3 points on the right are not affinely independent. They're affinely dependent. Or sometimes you might say these points are not in general position. They satisfy some very special geometric criterion, in this case that they all sit on a line. Right? So saying that points are affinely independent intuitively is like saying, oh, the points are put down in the plane or in Rn in a way that's generic. Right? It's not a special case. Okay? All right, so with that all in place, we can now define really what a simplex is. And this is going to be a geometric definition of a simplex. Right? We said before we want to distinguish between just talking about connectivity versus talking about shape and where things actually sit in space. This is a more geometric point of view. So we're going to say a k-simplex is the convex hull of k plus 1 affinely independent points, which we call its vertices. Okay, let's look at some examples. Well, let's start with the easiest case. We just have 1 point. Okay, what is the convex hull of a single point? What is the smallest convex set that contains a single point? This question really tests your understanding of the definition of a convex set, but a single point is already a convex set. So if I take any 2 points in that set, well, they have to be the same point, and I draw the line segment between them, well, it has to be a line segment that goes from that point to itself. That segment stays entirely inside the set. Okay, so a single point is convex in kind of a degenerate way. And so what that means is a zero simplex is just a point. It's a very, very fancy way of talking about a point. More interesting is, let's say we have two affinely independent points. Okay. So now, what does the convex hull of 2 points look like? Well, it looks like a line segment. Okay. So a 1 simplex is an edge. If I have 3 points that are affinely independent, what does the convex hull look like? What's the smallest convex set that contains those 3 points? Well, it's a triangle, right? So a 2 simplex is a triangle. By the way, why do we want to make sure that these points are affinely independent? Why couldn't we have just said a k-simplex is the convex hull of k plus 1 points? Well, there'd be a little bit of confusion then, right? Because if I have, for instance, 3 points that are all on the same line, and I take their convex hull, then I'll get a line segment rather than a triangle. So by making sure that they're affinely independent, I really know that 2 points give me a edge, 3 points give me a triangle, and so on. Okay? Finally, let's say we have 4 points, and now these points are in 3-dimensional space. Okay? They have to be in order to be affinely independent. I can't have 4 affinely independent points in 2D. Why not? Well, in order to have 4 affinely independent points in 2D, I'd need to have 3 independent vectors in 2D. And the fact that I'm in 2 dimensions means that I can always express every vector in a basis of just 2 vectors. Okay? So in order to talk about 4 affinely independent points, I have to be in 3 dimensions. What happens if I take a convex hull of these 4 points? What shape do I get? Okay, maybe a little harder to see, but what I get is a tetrahedron. What I get is a triangle where I've added an additional point and then taken the convex hull. Okay, so there we go. That's our idea of a simplex, our geometric picture of a simplex. And one thing we learned is that I can only have a simplex of a certain degree in a certain dimension, right? I can only have a 2 simplex in 2D, but not a 3 simplex. I can only have up to a 3 simplex in 3 dimensions, but not a 4 simplex, and so on. Okay? When talking about simplices, it's going to be really helpful to put coordinates on our simplices. And the most natural coordinates for a simplex are something called barycentric coordinates. So let's start out easy. Let's talk about just a 1 simplex. So for a 1 simplex, we can actually think of the 1 simplex as all weighted combinations of the 2 points, let's call them A and B, where the weights sum to 1. So I can think of all the points in the 1 simplex as 1 minus t times A plus t times B for some number t between 0 and 1. And if I draw out p of t for all values of t, I get this segment. Right? If t were equal to 1/4, I'd be here. If t were equal to 3/4, I would be here, and so on. Okay. We can, of course, generalize this idea. So more generally, any point P in a simplex sigma can be expressed as a non-negative weighted combination of the vertices where the weights sum to 1. So this white point, for instance, can be written as 2/10 P1 plus 4/10 P2 plus 4/10 P3. Right? You see it's a little bit closer to P3 and P2 because the weights are bigger than the weight for P1. In general, the simplex itself consists of all points that can be written as the sum from I equals 0 up through k of ti pi for some weights ti that, well, sum to 1 and are greater than or equal to 0. These weights, these values t sub I, are called the barycentric coordinates. And by the way, these combinations of points we're talking about are called convex combinations of points. Right? So in fact, we could have defined the convex hull as the set of all possible convex combinations of the points in the given set. That'd be another characterization. Okay. Here's one important example of a simplex, which is something called the standard n-simplex. So the standard n-simplex is the collection of all points sigma that have coordinates x0 through xn in Rn plus 1. And as always, these coordinates sum to 1 and are greater than or equal to 0. What does this look like? It looks something like this. Right? It has vertices along the coordinate axes, distance 1 along the coordinate axes. Right? And then you connect those vertices to get the simplex. This is also known, by the way, as the probability simplex. Why is that a natural name for this simplex? Well, because probabilities are non-negative and sum to 1. Okay, so you get the sense that simplices also, in some sense, have something to do with probability. All right, so that's a really close look at a single simplex, at a single mesh element, if you like. And now what we're going to do is we're going to connect up a bunch of simplices to get a mesh or a simplicial complex. Okay, so roughly speaking, a simplicial complex is a fancy name for a bunch of simplices. By the way, just a little bit of a comment on language. So the plural of simplex is not simplexes, it's simplices. Just like the plural of vertex is vertices and the plural of vortex is vortices. Okay? So anyway, a simplicial complex is a bunch of simplices, but it's not just a jumble of simplices. It has some specific properties that it's going to make this collection easy to work with. Okay? And in understanding what this collection looks like, we have to resolve some basic questions. In particular, how do we allow different simplices in this complex to intersect? A little bit of anatomy of a simplex. So a face of a simplex, sigma, is any simplex whose vertices are a subset of the vertices of sigma. So for instance, if we have a two-simplex, a triangle, with vertices P1, P2, and P0, then here are its faces. Right? I've offset these faces so that they're easier to look at. The faces really would be sitting right on top of the original piece of the simplex that they come from. Okay, but we have all the possible subsets. We have subsets of size 2 that give edges like P1, P2. We have subsets of size 1, P1, P2, P0, which give the vertices. And also, by the way, a face doesn't have to be a proper subset. So for instance, the face itself, the triangle itself, is a face of itself. By the way, is there anything else missing from this picture? Did we get all the subsets of that triangle? Or at least did we get all the subsets of the vertices? Well, essentially, yes. The thing that we kind of didn't say out loud is, well, the empty set is also sitting in this picture somewhere, the set of no vertices, right? The set of no vertices formally, technically, defines a simplex, a -1 simplex, okay? This is a technicality that sometimes makes things easier to write and sometimes it's just annoying. I think it's best to just not think too much about this empty set, but know that it's there. Okay. So we can now give a definition to a simplicial complex, at least a sort of geometric definition, one where we care about where things sit in space. So we're going to say a geometric simplicial complex is a collection of simplices where, well, for one thing, the intersection of any two simplices is a simplex, and two, every face of every simplex in the complex is also in the complex. Okay, so translating those words into pictures, here's an example of a simplicial complex. So what do we see? We notice, for instance, if we have two triangles, they meet at an edge or at a vertex. Or maybe we have a tetrahedron and a triangle. Their intersection is a vertex, right? So that first property is satisfied. And something that's not really evident from the picture, it's a little bit hard to draw, but basically we would say it's not just the tetrahedron that's in this complex, for instance, it's also the triangles contained in that tetrahedron and the edges of those triangles and the vertices of those edges, and the empty set. Okay, so if that's a simplicial complex, well, what's something that's not a simplicial complex? At least in this geometric sense, this is not a simplicial complex, right? Because, for instance, we have a pair of triangles that meet in a little segment that's not actually an edge. It's not something that connects two vertices of our simplicial complex. Okay? But we'll come back to this idea later. This picture is actually not generally very relevant for thinking about discrete differential geometry. Okay, so first a concrete example. Here's a very happy simplicial complex, and let's enumerate the vertices. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so just to make sure we understand the definition of a simplicial complex, let's list what are all the simplices in this simplicial complex. So just rattle some of them off. Well, we could start with the two simplices, the triangles, right? So we know that 6, 7, 9 and 7, 10, 8 are in this complex. Then we could go list all the edges. Okay, 2, 3, 3, 4, 4, 5, 6, 7, 7, 9, 9, 6, 7, 8, 8, 10, 10, 7. Those are all one simplices in this complex. We shouldn't forget, of course, about the zero simplices, the vertices. So just 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And if you like, we could also include the empty set. Okay. Now, one thing you notice about this description on the right of this simplicial complex is it does tell us pretty much everything about how this complex is connected up, right? But we didn't say in this list anything about geometry. We didn't give coordinates for these points, and we didn't give any other information like lengths or areas or angles, right? We just said something about how points are connected up. And so this kind of tells us that fundamentally, a simplicial complex really can be described in terms of its connectivity. That leads to the idea of an abstract simplicial complex. Okay? So to give a abstract definition, let's say S is a collection of sets. Very generic. Then if for each set sigma in S, all subsets of sigma are also contained in S, then S is an abstract simplicial complex. Okay? And a set sigma in S of size k plus 1 is an abstract simplex. Okay, this got, well, a lot more abstract, right? We're no longer talking about points in space or convex hulls or any of these pictures we've been drawing. We're really just saying a abstract simplicial complex is a collection of sets that have certain properties. You can take subsets and so forth. Okay, so maybe then this is a geometric simplicial complex, and well, this is a perfectly good abstract simplicial complex if you just ignore the way that it's sitting in space and only care about who's adjacent to who, which vertices are next to which other ones, and which ones form a triangle, which ones form a tetrahedron, and so forth. Okay, we just care about how things are connected and not how they're arranged geometrically. Okay, and this object, this abstract simplicial complex, is what provides a discrete analog for a topological space. It gives us a notion of how our geometry is connected up without worrying about what shape it is or where it sits in space. Okay. An important example of an abstract simplicial complex, which you might have encountered before, is a graph. An undirected graph G equal VE is an abstract simplicial 1 complex. Why do I say it's a 1 complex? Well, because the degree of the highest degree of any simplex is 1. We just have edges and we have vertices. Right? So the 0 simplices are vertices, the 1 simplices are the edges. Okay. Here's another example. Hopefully gets the idea across. This one we're really going to avoid drawing pictures, right? So we just say, let's consider the set S, where the points in this set look really funky, right? S is a collection of sets. What's in that collection? Well, there's the set 1, 2, heart, and 2, heart, smiley, and 1, 2, and 2, heart, and heart 1, and 2, smiley, and smiley, and heart, smiley, and 1, 2, heart, smiley, and also the empty set. Okay. So, question, is this set an abstract simplicial complex? And if so, what does it look like? Or how are things connected up? Okay. So the first thing you might do is just go to each set and check, are its subsets also in S? So I have the set 1, 2, heart. Can I find 1, 2, 2, heart, and heart 1 in this set? Sure. And by the way, because these are sets, I don't care about the ordering, right? It's heart 1 or 1 heart. Okay. What does it look like? How is it connected up? Well, I can always draw some picture depicting this abstract simplicial complex. So in this case, if I look at what's going on, okay, I have two simplices, 1, 2, heart, and 2, heart, smiley. I notice that they share a common face, 2, heart. Okay, so that sounds like a pair of 2 simplices, a pair of triangles sharing a single edge. And indeed, I can draw that out in the plane, for instance. Okay. But the important point is that vertices of our abstract simplicial complex no longer have to be points in space. They can represent anything at all, any kind of data. Okay. So before going on with more and more definitions, I just wanted to pause for a moment and mention very briefly an application that uses this idea of a simplicial complex to make sense of data. And there's actually kind of a whole field of topological data analysis. You could take a whole other course on this subject. And the idea is that you want to forget mostly about the geometry of the data, but really try to understand something interesting about what's going on in a system or a network or a data set by looking at its connectivity, first and foremost. Okay, so just one of many ideas in this area is an idea called persistent homology, which I'll try to explain briefly. So the motivating example here is I have just a set of points. Okay, literally I have a list on my computer of coordinates for these points. I know nothing else about them. But as a human observer looking at this plot of these points, you can tell, oh, okay, those look like some familiar letters, right? There's definitely some structure to this data. Well, how would you get your computer to recognize this structure? How could you determine, for instance, that there are 3 letters? How could you determine that, some of those letters are different from other letters? And how could you be sure that you got the answer right? So the very, very rough idea of persistent homology is to say, okay, I've got my points, and I'm going to grow some balls around each point. And then if 2 balls overlap, I'll connect them by a 1 simplex. If 3 balls overlap, I'll connect them by a 2 simplex, and so forth. Right? So something like this. These two balls get an edge. These other three balls get a triangle. Okay, and then I'm going to do this process of connecting up for an increasing ball radius. So for these points on the bottom, I can grow my balls bigger and bigger and bigger. And when two balls overlap, I make an edge. When three overlap, I make a triangle. Maybe I start making three simplices and so forth. Okay, and I start filling things in. And initially you notice, okay, the three letters get connected up in a way that you might expect. But then after a while, things get kind of too connected, right? The holes start getting filled in. The letters start getting connected to each other. So what's the conclusion? If you wanted to know how many letters, and it's going to play backwards here now. So if you want to know how many letters there are or which letters form a loop versus which ones don't, which ball radius should you trust? And the answer is you shouldn't trust any one radius, but instead you should track the birth and death of different features like connected components and holes and so forth. Right? So you can plot this information on what's called a persistence diagram, where you say, okay, the first time that this connected component consisting of, I don't know, these three particular points came into being, that's going to be my x-coordinate. And when those 3 points merged with another fourth point, that's when that component died and there was a new component. Okay? And so every point in your persistence diagram is going to be above the diagonal because, well, you have to be born first in order to die. Okay? And then you notice some things on this diagram that some points are really far from the diagonal, whereas some points are really close to the diagonal. What does that mean? What's the difference between these kind of events? Well, if you stop and think about this for a minute, you realize, well, it must be that, or it's likely that features that persist for a long, long time are real, right? We have these three letters, and at some point, all the points in each letter get connected up, and they kind of stick around for a while before finally merging with each other. Right? Whereas the connected components we have at the beginning, just 2 points getting connected by an edge, well, that quickly dies, and that edge becomes a triangle, and that triangle becomes, part of some other simplex and so forth. Okay, so features that persist for a long time are likely real. In this case, we have 3 letters. Features that quickly appear and then disappear are likely noise. Right? They just have to do with how particularly you sampled the data. Okay, so really quite neat idea, and people have taken this in all sorts of directions. Right? This is just one very kind of special instance of this. So one nice application in material science is characterizing glass. So you can ask a question: if I look at the locations of a bunch of atoms in a material, can I tell you kind of what state it is? Maybe it's not so hard to determine whether it's a solid or a liquid or a gas. But glass was kind of a funky material. People didn't have a great way of characterizing quantitatively, okay, well, what arrangement would you call glass? However, if you plug in this machinery of persistent homology and draw one of these persistence barcodes, what people discovered is that there's a very, very strong feature that shows up in glass that doesn't show up in kind of just randomly arranged atoms. So if you look at this persistence barcode on the bottom right, there's this strong feature on the kind of left side, this orange vertically stretched blob, something that really shows up strongly in glass. And there's a citation down here if you're interested. So something that you could get by kind of looking at simplicial complexes and topology that you don't see using other data analysis tools. And there's tons of other things people do with this. I mean, the idea of having points in Rn and looking at their structure is pretty generic. So there's things that are very concretely geometric. So for instance, if you want a signature for a point on a surface, you want to know, okay, I have a point on the middle of the middle finger, and I want some kind of signature or data that tells me that I'm at that point versus some other point, like the thumb. Well, what I can do is start growing a ball around that point on the surface, And there will be certain interesting events, like that ball will start growing and then it'll run into itself and it'll cut off the tip of a finger, but eventually the tip of the finger will get covered and so forth. And by recording the times of those events, you get a signature for this point. If you now go to another hand and measure its signature and it looks like this, it has the same kind of persistence barcode, you can say, aha, I bet you that's a point on the middle of the middle finger. Okay? And people play similar games to understand, for instance, the network of neurons in the brain, helping to discriminate between healthy brains and brains with some kind of perhaps debilitating disease. Or you might look at persistent homology or do topological data analysis on social networks, right, or other networks that appear naturally, and trying to understand, what can you understand about a community, about a member of that community by looking at this kind of connectivity information rather than any particular data sitting on that graph. Okay? And much, much more. People use this machinery for all sorts of things. Identifying cancer, classifying players in basketball, compressing images, all sorts of stuff. Okay. So to get back to our main story, if we want to analyze simplicial complexes in this more detailed way, then we need to talk a little bit about the anatomy of a simplicial complex, different parts and pieces. One idea is the closure. So if I have a set of simplices in my complex, I can look for the smallest simplicial complex containing that given set. Okay? Really simple example, let's say my set is just a single triangle, a single two-simplex, and a single edge. Right? The union of a triangle and an edge. What's the closure? Well, the important thing to remember here is a simplicial complex contains all of its faces. So the closure of this set is going to be not just the triangle and the edge, but also all the edges of that triangle, all the vertices of that triangle, and all the vertices of the edge. Okay? The star, a different operation, is going to be the union of simplices containing a given subset of simplices. Okay, so for instance, if I have a vertex, then the star of that vertex is, well, it's all the simplices that contain that vertex. It's all the triangles that touch the vertex and all the edges that touch that vertex. But you notice it's not, for instance, all the edges that go around the boundary of this dark blue region, because those edges don't contain my initial vertex. Okay? And finally, I have the link. So the link is the closure of the star minus the star of the closure. I just compose these two operations. Why do I want to do this? Well, a really common thing is I'm looking at a vertex. Its link is going to look something like this. It's going to look like the loop that goes around the vertex. Right? So as I said just a moment ago, the star doesn't contain this loop of edges. If I want this loop of edges, I can take the star, take its closure. That's going to give me all the triangles and all the edges incident on the vertex and all the vertices and edges of that set. Right? And then just subtract the star of the closure. Subtract the interior, and I get the boundary. Okay? So in general, this language, closure, star, link, it's kind of a shorthand for saying which piece of the mesh am I talking about. Right? Rather than saying, oh, well, I'm talking about the set of elements I get by taking all the triangles touching the vertex and all the edges touching the vertex and doing, right now you just have a shorthand to say, oh, I'm talking about the link. I'm talking about the star, and we'll use that in a moment. Okay. Also, some notation that'll be useful. So for a simplicial 1 complex, for a graph, we often write G is equal to VE, right? G is a graph with vertices V and edges E. For a simplicial 2 complex, for a triangle mesh, we're going to write K equals VEF. Okay, so V are the vertices, E are the edges, and F are the faces. Now, this is a little bit confusing because we have this other notion of a face. Generically, a face of any simplex is, a simplex made by a subset of the vertices of that simplex. That's not what we mean here. So when we're talking about a 2 complex, a face is always going to mean a top degree face, a triangle. By the way, why do we write this as K? Well, in German, complex is spelled with a K. Okay. So now we're going to give just a little bit more structure to our simplicial complex. We're going to give it a little bit more data that turns out to be extremely useful when we start doing calculations on geometry. Okay? And that's a notion of orientation. So before giving a precise definition of orientation, I just wanted to show a few pictures to get you in the mental frame of thinking about orientation and realizing that there are a lot of things that you encounter in your day-to-day life, or also maybe some things you don't, where orientation plays an important role. Maybe the most important one is that some streets are oriented. If you have a one-way street, you can go this way and not that way. Right? It's a directed street. Likewise, you might need to keep a box at a certain orientation. And then you might have seen examples of funky surfaces like the Mobius band that you would say, oh, that it only has one side. It doesn't have 2 orientations like a piece of a cylinder does. There's also physical phenomena where orientation is kind of an interesting thing to talk about. So, for instance, in liquid crystals, you have little particles that can take either orientation. Okay, unlike magnets, maybe, that have a preferred orientation. Okay, so just to give a sense, what do we mean when we use this word orientation? So a little more precisely, let's talk about the orientation of a 1 simplex. So the basic idea is we are just saying, do we want our 1 simplex AB to go from A to B or from B to A, right? Like this or like that. And so what we can do is, rather than writing an unordered set AB in curly braces, we can now write an ordered tuple AB or BA in round parentheses. Why do we care? Why do we want to assign orientation to something like an edge? Well, eventually, this is going to be really useful for recording integrals. So where we're headed is to build up something called discrete exterior calculus, where we're going to integrate along edges. And when you integrate, it matters very, very much whether you integrate from A to B or B to A, because the sign flips. Okay, but we're not quite there yet. So to continue with our story about orientation, we can also think about the orientation of a 2 simplex. For a 2 simplex, the orientation is given by the winding order, sort of the vertices. So if I have a triangle like this, well, you could think of the vertices as going in counterclockwise order like that, or in clockwise order like that. Right? If we label these A, B, C, then we could say we have a tuple or a triple A, B, C, or A, C, B. Those are now inequivalent, right? And in fact, there are other tuples we could write that have counterclockwise order, BCA, CAB. There are other tuples we could write that have clockwise order, CBA and BAC. Okay? So really, an oriented 2 simplex can be specified by a 3 tuple, and circular shifts describe the same oriented 2 simplex. If you want to be a bit more sophisticated about this, you could say an oriented 2 simplex is an equivalence class of 3 tuples, where 2 tuples are equivalent if they're related by a circular shift. Okay, so let's take that all the way to the orientation of a k-simplex. How do we define orientation in general? Well, it's going to be hard to draw little arrows or clockwise, counterclockwise widgets or whatever as we keep going up in degree. But we can use an idea that's similar to the idea that we used for the 2 simplex. We can say an oriented k-simplex is an ordered tuple up to even permutation. Right? Even permutation meaning we do an even number of swaps of elements of our tuple. Okay? So Because of that, we know that we always have two possible orientations for a k-simplex, because we can either do an even or an odd number of permutations of the vertices. Okay? And just linguistically, we'll say that if we start with the simplex with vertices 0 through k, and we do an even number of permutations, then that simplex has positive orientation. It has the same orientation as the sort of canonical simplex. Otherwise, it has negative orientation. Okay? Always important to think about the kind of corner cases. So in particular, what is the orientation of a single vertex? What does that mean? Right? We just have this one vertex. What is its orientation? What does that mean? How do we orient a vertex? Well, one thing we can say for certain is that there's only one permutation of the vertices. Right? There's just this one tuple that contains A, and the only thing we can get by permuting its vertices is the same thing again. Right? So there's only one orientation. A vertex is always positively oriented. Okay? So as I mentioned, it's hard to draw pictures as k gets large. Like maybe for a tetrahedron, we can still sort of do it by either drawing normals sticking out of the tetrahedron or normals sticking into the tetrahedron. But it's still easy enough to apply the definition. Right? So we could say, all right, if we enumerate the vertices of the tetrahedron, 1, 2, 3, 4, then the even permutations, the positive oriented simplices are 1, 2, 3, 4, 1, 3, 4, 2, 1, 4, 2, 3, and so on. And the odd or negative ones are 1, 2, 4, 3, 3, 1, 4, 2, 1, 3, 2, 4, and so forth. Okay. It's much easier, of course, if I want to tell you which one I'm talking about, to just pick a single representative, right? So I could just say, oh, plus sigma, that's 1, 2, 3, 4, and minus sigma, that's 1, 2, 4, 3. Okay. Well, before we had simplices and simplicial complexes. Now we have oriented simplices. Of course, we must be able to define a oriented simplicial complex. So what does that mean? Well, we said an orientation of a simplex is an ordering of its vertices up to even permutation. One can specify an oriented simplex via one of its representative oriented tuples. Okay, this is what we've said so far. So then an oriented simplicial complex is a simplicial complex where each simplex is given an ordering. That's a lot of words to say simply that an oriented simplicial complex is just an ordinary simplicial complex, except, well, we draw a little arrow on each simplex. Right? So here's one particular example. We have these two triangles and edges and vertices. And for each triangle, we've decided, okay, do we want the clockwise or counterclockwise ordering of the vertices? For each edge, do we go one way or the other? Okay. And by the way, the first question anybody ever asks about this is, well, do these all have to be sort of consistent in some way? If, for instance, I'm going clockwise around a triangle, do the edges bounding that triangle also have to go clockwise? No, not at all. Right? You can pick these completely arbitrarily. The oriented simplicial complex is simply an assignment of some orientation to each simplex, period. You can assign whatever you want. We can write this simplicial complex or this oriented simplicial complex out as a set, right? So as before, we still have the property that if I have a triangle, then all of its edges have to be in the complex. If I have an edge, its vertices have to be in the complex, and so forth, right? Except that each of those elements is given an orientation. Each of them is written now as an ordered tuple rather than a set. Okay? Here is a different oriented simplicial complex. It has the same triangles, edges, vertices, but different orientations, right? So we write it out like this, and you notice, for instance, ACB has changed to ABC. Okay. Now, I said just a moment ago, it doesn't matter whether the orientation of edges agrees with the orientation of triangles and so forth, but we can talk about that notion of agreement in a precise way. We can talk about the relative orientation of two simplices. Okay? In particular, we can say two distinct oriented simplices have the same relative orientation if the two maximal faces in their intersection have opposite orientation. Okay, maximal faces means consider their intersection and take the simplex of biggest degree in their intersection. So for example, let's say I have two triangles that intersect along an edge, right? Then these two triangles have the same relative orientation. Why is that? Well, look at the edge BC. In triangle ABC, that edge goes from C to B. In triangle BCD, that edge goes from B to C. If we draw two triangles like this now, they have different relative orientation because both triangles give the edge BC the same orientation. It's a little bit confusing, right? In order to have the same relative orientation, the two faces in the intersection have to have opposite orientation. So maybe helpful to write this out, right? We can say on the left, we have triangle ACB, and the edge of that triangle goes from C to B. For triangle BCD, the edge goes from B to C. Since CB is equal to minus BC, we actually say they have the same relative orientation. Right? And you can kind of see from the picture this is the right idea. If they have the same relative orientation, that means in this case both triangles are going clockwise. Okay? Similarly, if I write out the triangles for the other oriented simplicial complex, I see that the shared edge has the orientation BC in both cases, and well, BC is the same as BC, so these actually have different relative orientation. One natural question you might ask is, can I always assign an orientation to my simplicial complex so that I get consistent relative orientation on shared faces? And the answer is, well, sometimes. If we think back to this picture of the cylinder versus the Mobius band, right? If we triangulate those, then in one case we can, and in one case we can't. And so in fact, this information, this local information about orientation, actually can tell us something globally about the topology of the shape that we're looking at. Okay, so we'll have a lot more to say about orientation as we go on and talk about discrete exterior calculus.